Every time you pass by a railway track, you've walked over one of engineering's most ingenious secrets, countless carefully engineered stones that literally hold our transportation system together. These aren't random rocks scattered by nature. Every single stone has been precisely crushed, sized, and shaped according to strict specifications that most people never realize exist. What you're looking at underpins modern railroads worldwide and prevents derailments that would otherwise occur without this critical foundation. High-traffic railway lines replace this ballast every 15 to 20 years to maintain safety standards, revealing just how essential these seemingly ordinary stones are to keeping trains running safely across the globe. The hidden science behind stone selection. But what exactly makes these stones so special isn't immediately obvious to the naked eye. Engineers spend years perfecting the exact specifications through a selection process that involves far more science than most people realize. Railway ballast stones must pass through rigorous testing protocols that would surprise anyone who thinks these are just ordinary rocks. Engineers examine every aspect of these materials, from their chemical composition to their physical properties, before approving them for railway use. Each stone must meet incredibly precise requirements for angularity, surface texture, and internal structure that determine whether a railway system succeeds or fails. The angularity measurement focuses on ensuring stones have multiple fractured faces rather than smooth surfaces. This requirement isn't arbitrary. Stones with insufficient fractured faces lack the mechanical interlocking properties essential for track stability. Surface texture requirements focus on roughness values measured using specialized equipment that evaluates how much friction each stone can generate when pressed against neighboring particles. The process begins in quarries, where geologists identify rock formations with specific mineral compositions and hardness ratings. Suitable ballast materials typically include granite, basalt, and quartzite, each offering different advantages for railway applications. Granite, with its interlocking crystal structure, provides excellent durability and resistance to weathering. Basalt offers superior resistance to freeze-thaw cycles that can damage track foundations in cold climates. Quartzite delivers exceptional hardness but requires more energy to crush into proper sizes. Geologists use core sampling to test rock formations at various depths, ensuring the entire quarry can produce consistent quality material. Different types of these materials are tested for their ability to withstand millions of compression cycles without breaking down into dust. Laboratory testing involves subjecting stone samples to repeated loading cycles that simulate decades of train traffic according to research protocols. The testing equipment applies loads at frequencies matching typical train passage rates. These materials must maintain structural integrity through millions of loading cycles, though their higher cost makes premium stones suitable mainly for heavy freight corridors where the investment justifies the performance benefits. The crushing process itself is an engineering marvel, using specialized machinery that creates the optimal angular shapes rather than rounded pebbles. Primary crushers break quarried rock into pieces roughly 150 to 200 millimeters in size. Secondary crushers reduce these chunks to the 50 to 75 millimeter range required for most railway applications. The crushing equipment uses impact and compression forces specifically designed to create fractured surfaces rather than smooth breaks. Jaw crushers apply slow, steady pressure that produces fewer fine particles. Impact crushers use high-speed hammers that create more angular fragments with better interlocking characteristics. Quality control laboratories test each batch using the Los Angeles abrasion test, which measures how much the stones will degrade under mechanical stress. This test involves placing stone samples in a rotating drum with steel spheres, then measuring material breakdown after standardized testing cycles. Quality ballast materials typically show low abrasion values, meaning minimal material degrades during testing. Premium ballast materials achieve even better performance ratings. Materials exceeding acceptable abrasion limits are considered unsuitable for mainline railway applications. Temperature resistance is crucial since these stones must maintain their integrity in climates ranging from Arctic conditions to desert heat. Thermal cycling tests expose stone samples to extreme temperature ranges through multiple heating and cooling cycles to simulate years of seasonal temperature variation. Stones that crack or spall during thermal cycling are rejected. Granite generally shows excellent thermal stability due to its uniform crystal structure. Basalt performs well in cold climates but can become brittle in extreme heat. Quartzite demonstrates superior thermal resistance across all temperature ranges. The grading system ensures that stone sizes follow precise mathematical distributions with specific percentages of different diameter ranges. Standard ballast grading requires careful controlled particle size distributions to maintain proper mechanical properties. The largest particles provide structural stability. Medium particles fill gaps and enhance interlocking. The absence of very small particles maintains proper drainage characteristics. This precise size distribution prevents segregation during transport and placement while optimizing mechanical properties. Even the surface texture is controlled through specialized crushing techniques that create the right amount of roughness for optimal interlocking. Crusher settings determine the amount of surface area created during the fracturing process. Higher crusher speeds generate more surface texture, but also produce more fine particles that can clog drainage systems. Lower speeds create smoother surfaces with reduced interlocking capability. Engineers adjust crusher parameters to achieve optimal surface roughness values. Surface texture measurements use laser scanning equipment that maps microscopic surface variations across representative stone samples. Production quality control extends beyond individual stone properties to batch consistency. Automated sampling systems collect representative samples throughout production cycles. Chemical analysis ensures consistency within acceptable ranges. Particle size analysis uses mechanical sieving to verify grading compliance. Shape analysis employs digital imaging systems that measure angularity and surface texture of thousands of particles per sample. Statistical process control tracks all parameters over time, triggering production adjustments when values drift outside specification limits. Specialized testing equipment evaluates additional properties that affect long-term performance. Petrographic analysis examines rock sections under microscopy to identify potentially harmful mineral phases. Some minerals can cause chemical degradation over time. Others can expand when wet and disrupt track geometry. Soundness testing simulates chemical weathering processes. Stones that show excessive degradation during soundness testing are rejected for railway applications. This scientific approach to stone selection reveals why railway ballast represents one of the most precisely engineered bulk materials on Earth. The specifications governing ballast production are more stringent than those for many construction materials. Every aspect of ballast stones, from their mineral composition to their surface texture, is controlled through rigorous testing and quality assurance programs. This level of precision explains why ballast stones look remarkably similar regardless of their geographic origin. They all must meet the same demanding engineering requirements. Yet the real engineering magic happens not in the individual stones themselves, but in how these carefully crafted pieces work together once they're placed on the track. The interlocking mystery that prevents disasters. The secret to railway stability lies in a phenomenon that engineers call mechanical interlocking, and it's more complex than most people realize. This interlocking system operates on principles that go far beyond simple friction between stones. When trains weighing thousands of tons travel at high speeds, the forces trying to push tracks out of alignment are enormous. The ballast stones must work together as a unified system to resist these forces, and mechanical interlocking provides the mechanism that makes this possible. When you look closely at ballast stones, you'll notice their jagged, angular surfaces aren't accidental. They're specifically designed to grab onto neighboring stones. These angular surfaces create contact points where stones physically hook together. Each contact point generates friction forces that resist movement in multiple directions. The jagged edges work like tiny mechanical fasteners, preventing stones from sliding past each other when subjected to external forces. Engineers design crushing equipment specifically to create these angular surfaces, rejecting any production methods that would create smoother, more rounded particles. This interlocking effect creates what engineers call a friction matrix, where each stone interlocks with its neighbors in a three-dimensional network. The friction matrix operates through direct contact between adjacent particles and extends throughout the entire ballast layer. When one stone experiences force, that force transfers to neighboring stones through the contact points. These neighboring stones then transfer forces to their neighbors, creating a network effect that distributes loads across thousands of individual particles. The three-dimensional nature of this network means that forces can be redirected in any direction needed to maintain stability. The angular coefficient, measured in degrees, determines how effectively stones resist lateral movement when subjected to dynamic loads from passing trains. Engineers measure angular coefficient by analyzing the shape of individual stones using digital imaging systems. Stones with angular coefficients above 150 degrees provide optimal interlocking performance. Lower angular coefficients indicate more rounded shapes that reduce interlocking effectiveness. The measurement process involves photographing stones from multiple angles and calculating the average angle between adjacent surfaces. Quality control systems continuously monitor angular coefficients during production to ensure specifications are met. Laboratory tests show that rounded river stones, despite being the same material, provide only 30% of the stability of properly crushed angular ballast. These comparative tests use specialized equipment that applies lateral forces to ballast samples while measuring displacement. River stone samples typically show lateral movement of 15 to 20 millimeters under standard test loads. Angular crushed stone samples show movement of only 4 to 6 millimeters under identical conditions. The dramatic difference demonstrates why railway specifications require crushed stone rather than naturally rounded alternatives, even when the source rock material is identical. The interlocking mechanism works through friction at contact points and micromovements within voids that distribute forces across thousands of contact points. Friction develops at every point where stones touch each other. The angular surfaces increase the contact area and create higher friction coefficients than smooth surfaces would provide. Mechanical interference occurs when the irregular shapes of stones prevent them from moving past each other. Load transfer happens when forces applied to one stone get transmitted to neighboring stones through the contact points. This combination creates a stable foundation that responds to loads as a unified structure rather than as individual particles. When trains apply lateral forces during cornering or braking, the interlocked stone matrix acts like a solid foundation that can resist movement. Cornering forces develop when trains navigate curves at speed. These forces try to push the outer rail and its supporting structure outward from the curve. Braking forces create longitudinal loads that attempt to push the entire track structure forward. The interlocked ballast matrix distributes these forces across wide areas, preventing localized failures that could lead to track misalignment. Emergency braking situations can generate forces exceeding normal operating loads by factors of 3 or more, making the interlocking system critical for safety. Computer simulations reveal that without proper interlocking, railway tracks would shift laterally by several centimeters after just a few train passages. Advanced finite element modeling simulates the behavior of ballast systems under various loading conditions. The simulations model individual stones as discrete elements with contact forces calculated at each interaction point. Results show that non-interlocking spherical particles allow track displacement of 40 to 60 millimeters after simulating 100 train passages. Properly interlocked angular particles limit displacement to less than 5 millimeters under identical conditions. These simulations help engineers optimize ballast specifications for different operational requirements. The ballast also dampens much of the wheel rail vibrations through energy dissipation at countless contact points throughout the stone matrix. When trains pass over tracks, they generate vibrations that would otherwise transfer directly to the ground and surrounding structures. The interlocked stone network absorbs these vibrations through friction and micromovements at contact points. Each contact point acts as a small energy dissipator, converting vibrational energy into heat through friction. The cumulative effect of thousands of these contact points creates significant vibration reduction that improves passenger comfort and reduces structural stress on nearby buildings. The breakdown of this interlocking system, often caused by stone wear or contamination, is responsible for many railway maintenance issues worldwide. Stone wear occurs gradually as repeated loading causes small particles to break off from contact points. These fine particles accumulate in void spaces between stones, reducing the ability of larger particles to interlock effectively. Contamination from external sources like vegetation, soil infiltration, or spillage from trains creates similar problems. Fine contamination acts like lubrication between stones, reducing friction and mechanical interference. Understanding this interlocking mystery explains why railway engineers are so particular about ballast specifications and why shortcuts in stone selections lead to catastrophic track failures. The mechanical interlocking system represents the foundation of railway safety and reliability. Without proper interlocking, trains would be unable to operate at current speeds and loads. Yet this sophisticated interlocking system is only the beginning of how ballast stones protect railway infrastructure. The real test comes when massive trains bearing thousands of tons roll over these carefully engineered foundations. Load distribution engineering marvel. When a 6,000-ton freight train thunders over railway tracks, the forces involved will crush most surfaces, but ballast stones perform an engineering miracle. The weight of these massive locomotives and their cargo creates pressures that would devastate concrete, asphalt, or virtually any other surface material. A single freight car loaded with iron ore can weigh 125 tons, and modern freight trains routinely pull 100 or more of these cars. The total weight pressing down on the rails reaches levels that would cause immediate structural failure in most construction materials. Yet ballast stones handle these enormous loads day after day, year after year, without catastrophic failure. The load distribution mechanism works through a principle called stress diffusion, where concentrated wheel loads spread outward through the stone matrix. Engineers use mathematical models to calculate how forces propagate through granular materials like ballast. The stress diffusion follows predictable patterns based on soil mechanics principles developed over decades of research. When a train wheel applies force to a rail, that force transfers through the rail to the sleeper below. The sleeper then applies that concentrated force to a relatively small area of ballast stones directly beneath it. These stones immediately begin distributing the load to neighboring stones through their contact points. Each railway sleeper concentrates the weight of an entire train car into a relatively small contact area, creating pressures that would exceed the bearing capacity of most soils. A typical concrete sleeper measures approximately 2.5 meters long and 0.3 meters wide, creating a contact area of roughly 0.75 square meters with the ballast below. When a 125-ton freight car passes overhead, this sleeper must transfer that entire weight through its small contact area. The resulting pressure can reach 15 to 20 tons per square meter directly beneath the sleeper. Natural soil can typically support only 2 to 5 tons per square meter before failing, making direct placement of sleepers on soil impossible for heavy railway operations. The ballast layer acts like a sophisticated load spreading system, taking point loads of up to 25 tons per square meter and distributing them across much larger areas. The load spreading occurs through the natural mechanics of granular materials under compression. As pressure applies to the top layer of stones, these stones compress slightly and transfer forces to stones below and around them. Each successive layer of stone spreads the load over a wider area. By the time forces reach the bottom of the ballast layer, they have spread across areas many times larger than the original contact area. This spreading effect reduces pressure on the underlying soil to levels it can safely support. The depth of the ballast layer, typically range from 25 to 30 centimeters, is calculated based on soil-bearing capacity and expected train loads using complex geotechnical formulas. Engineers use the Boussinesq equation and other stress distribution formulas to determine optimal ballast depth for specific conditions. Soil-bearing capacity testing involves taking core samples and conducting laboratory tests to measure how much pressure the soil can withstand. Train load calculations consider not just static weight, but also dynamic forces from acceleration, braking, and track irregularities. The formulas account for safety factors that ensure the ballast system can handle loads significantly higher than normal operating conditions. Advanced finite element analysis shows how load distribution efficiency depends on stone size gradation, with specific ratios of large to small stones optimizing the spreading effect. Computer modeling divides the ballast layer into thousands of small elements and calculates stress distribution to each element. These models reveal that uniform stone sizes create less effective load distribution than carefully graded mixtures. Large stones provide structural framework and resist major loads, while smaller stones fill gaps and improve contact between larger particles. The optimal gradation typically includes 60% large stones, 35% medium stones, and 5% small stones. This distribution maximizes load spreading while maintaining adequate drainage properties. The void spaces between stones rather than being. Wasted space actually contributes to load distribution by allowing stones to slightly rearrange under pressure. When trains apply loads, the ballast stones compress slightly and rearrange to better distribute forces. This rearrangement allows the stone matrix to adapt to changing load patterns and maintain optimal contact between particles. The void spaces also provide room for this movement without creating permanent deformation. Laboratory testing shows that ballast with proper void ratios can handle 30% higher loads than densely packed ballast with minimal void space. Dynamic loading from moving trains creates additional challenges as the ballast must distribute not just static weight but also impact forces. Moving trains generate impact forces when wheels encounter rail joints, switches, or track irregularities. These impact forces can exceed static loads by factors of 2 or 3. High-speed trains create additional dynamic effects from wheel-rail interaction at elevated speeds. The ballast system must absorb and distribute these dynamic forces without allowing permanent track displacement. Impact forces occur when train wheels encounter discontinuities in the track structure. Rail joints create vertical impacts as wheels transition from one rail section to another. Switch points generate both vertical and lateral impact forces as wheels change direction. Track irregularities from settlement or wear create additional impact loading. These impacts can generate force spikes reaching 40 to 50 tons per square meter instantaneously. The ballast system must distribute these extreme loads quickly enough to prevent damage to underlying structures. The stone matrix accomplishes this through rapid force transmission between interlocked particles. Without proper load distribution, the subgrade soil beneath ballast would fail, leading to track settlement, alignment problems, and potential derailment. Soil failure typically occurs through bearing capacity exceedance or excessive settlement. Bearing capacity failure happens when applied loads exceed the soil's ability to resist shear forces. This type of failure can occur suddenly and create dangerous track conditions. Excessive settlement develops gradually as soil compresses under repeated loading. Settlement creates track geometry problems that require expensive maintenance and can limit train speeds. This load distribution system represents one of the most effective and economical foundation technologies ever developed for heavy infrastructure. The ballast system handles loads comparable to those supported by concrete foundations at a fraction of the cost. Unlike concrete foundations, ballast systems can be easily modified, repaired, or relocated as operational requirements change. The granular nature of ballast provides inherent flexibility that accommodates thermal expansion, ground movement, and structural settlement. Yet distributing these massive loads is only part of what makes ballast stone so remarkable. The real engineering sophistication becomes apparent when you consider vibration control technology hidden in plain sight. Every train passage creates a complex symphony of vibrations that could destroy track infrastructure. Yet ballast stones operate as an invisible dampening system that most people never recognize. These vibrations originate from multiple sources during normal train operations. Wheels rolling over rail joints generate impact vibrations every few meters as trains travel. The continuous interaction between steel wheels and steel rails produces high-frequency vibrations throughout each journey. Engine vibrations from diesel locomotives or electric motors transmit through entire train consist into the track structure. Braking systems add additional vibrational loads when trains decelerate or stop. Even passenger movement inside train cars contributes to the overall vibration burden that track systems must absorb. The vibration control mechanism functions through energy dissipation, converting kinetic energy from train movement into heat via interparticle friction. This energy conversion occurs at thousands of contact points between individual ballast stones. When vibrations enter the ballast layer from above, they cause microscopic movements between stones. These tiny movements create friction at each contact point, and friction always converts kinetic energy into thermal energy. The heat generated dissipates immediately into the surrounding environment, but the cumulative effect of millions of these friction events absorbs substantial vibrational energy. The physics behind this energy dissipation involves multiple mechanisms operating simultaneously. Direct friction occurs when stones slide against each other under vibrational stress. Rolling friction develops when stones rotate slightly at their contact points. Deformation friction emerges when stones compress and decompress elastically under cyclic loading. Each mechanism contributes to overall energy absorption, though direct sliding friction typically provides the largest contribution. Engineers calculate expected energy dissipation using material properties and contact mechanics, allowing them to optimize ballast designs for specific operational requirements. High-speed rail systems operating at speeds exceeding 300 kilometers per hour create vibration frequencies that can resonate with track components and cause structural failure without proper dampening. These high-speed operations generate vibrations across wide frequency spectrums. Low-frequency vibrations, typically below 20 Hz, come from spacing between train cars and major track irregularities. Mid-frequency vibrations ranging from 20 to 200 Hz result from wheel-rail interaction and rail joint impacts. High-frequency vibrations above 200 Hz develop from surface roughness on wheels and rails. The most dangerous vibrations occur when their frequencies match natural resonant frequencies of track components. Resonance becomes particularly problematic because it amplifies vibration magnitudes far beyond normal levels. Rails have natural frequencies around 1000 Hz for vertical bending and 500 Hz for lateral movement. Sleepers typically resonate at frequencies between 100 and 300 Hz depending on their material and support conditions. When train-generated vibrations match these natural frequencies, resulting amplification can exceed safe stress levels in track components. The ballast layer must absorb these resonant vibrations before they build to destructive levels. The ballast layer functions like a mechanical filter, absorbing high-frequency vibrations while allowing tracks to remain stable under dynamic loading conditions.